right. So the 7 problems I'm going to be doing. First is Euclid's lemma. Prove if GCD of AB equals 1 and A divides BC, then A divides C. Number 2, prove if x squared is odd, then x is odd. Number 3, prove x times 0 equals 0. Number 4, prove if x times y equals 0, then x equals 0 or y equals 0. Number 5, prove log base 27 of 14 is irrational. Number 6, the fundamental theorem of arithmetic. And number 7, the quotient remainder theorem. All right, so the first one here is the Euclid's lemma. Prove if GCD of AB equals 1 and A divides BC, then A divides C. Okay. So to start, we're going to write out a couple definitions that we're going to use. All right. So the definitions are just going to be explanations of all the mathematical terms except those that are undefined. Okay. So we're going to say integers, and we'll define integers as a whole number that can be positive, negative, or 0. Okay, so integers uses the symbol z, as so, and it includes 0, -1, 1, so we can go -2 and onward, okay? And then we can do 2 and further after that, okay? So it's a set of all those integers, all right? So we're gonna do, next we'll do the divisor. Okay, so when we're explaining the definition of a divisor, we're gonna say integer d is a divisor of n if, so IFF, if and only if, n equals dq for some integer q. Okay. Now, the next one we're going to do, we're going to explain common divisor. Oh, I'm going to go back to that black marker. So the next definition, common divisor. And when we're defining common divisor, we're going to let A and B be integers. So we're going to say exist in Z. So A and B are integers. We're going to say M is a common divisor of A and B if M is a divisor of A and M, let's go with blue again, M is a divisor of B. All right. So we have these three definitions so far, okay? Just to avoid writing down here, all right? We'll take note of these and just know that we'll use them in this proof, all right? Going to erase this here. All right. So the next definition we're going to define the greatest common divisor, or also labeled by the acronym GCD. Okay. So again, we're going to start similar to the last one. We're going to let A and B be integers, where A and B are not equal to 0. Okay? So M is a GCD of A and B if M equals GCD AB and GCD A divided by M, B divided by M equals 1. Okay? Also, we're going to say A over M, so this value, and B over M are relatively prime. Also, M is the largest. Let's make that a little cleaner. M is the largest integer that divides A and B. Okay. So there we go. Those are the definitions that we're going to need. We're going to need integer, divisor, common divisor, greatest common divisor. All right. So now we're going to go through some theorems that we're going to need. All right. So when we're talking about theorems, we're saying a mathematical statement that can be proven to be true. All right. So the theorem that we're going to be using in this proof is the Bezout's identity theorem. And this theorem states, suppose A and B are integers such that, we'll leave it there, okay? Let GCD of AB equal G. Now we're going to say then AX plus BY equals G for some integers X and Y. Okay? So the Bezout's identity theorem, suppose A and B are integers, let GCD of AB equal G, then AX plus BY equals G for some integers X and Y. Okay? So now we have all the definitions and theorems that we're going to need to solve this proof here. All right, so now we can get started on the proof. Okay? So if GCD of AB equals 1 and A divides BC, then A divides C. So our goal at the end of this proof is to be able to say that A divides C. All right? So we're first going to assume GCD of AB equals 1 and A divides BC. Okay? So we're first going to use the Bezout's identity theorem. So using Bezout's identity theorem relating to GCD, we can say, relating to GCD, 1 equals AX plus BY for some integers X and Y. Okay? Now, by definition of divisibility, so this is the first portion, okay? So second, we're going to say, by definition of divisibility, BC equals AK for some integer K. Okay? So we use Bezout's identity theorem, divisibility. All right? Now we're going to get to the next step. Okay, so then, knowing that our goal is A divides C, we know that C is going to be equal to A times some integer, okay? So when we're going through this proof, we're first going to say C, okay? And we know by multiplicative identity that C equals C times 1. Okay? So, using substitution, we know that for this example, 1 equals ax plus by. So C equals C times ax plus by. Alright, that's just by substitution. Okay, let's put a little star here. Alright, that's where we got this from. So when we go back later, we'll understand right where we got it. Alright, so we actually don't need to keep bringing this down. Alright, so now we're going to say, we're going to distribute using distributive law. So CAX plus CBY. Okay? So that's just by distributive law. Alright, let's write that. Law. Okay? Now, the next part that we have here, BC equals AK. So we want to be able to pull out or replace and substitute the BC for AK. Alright, so we see right here the CAX. Alright, we'll bring that down. Now we have BC times Y right there. Alright. Now, we're using substitution again. X plus AK. Let's put that in the blue. Alright. AKY. Alright, and that's by substitution. Okay. Ran out of space in there a little bit. That's okay. Alright, so now by factoring out an A, okay, we're going to get A times CX plus KY by factoring. Alright. And exactly like what we're looking for here, it's C equals A times an integer. Alright, so C equals A times J, we'll say, for this problem. Alright, where J equals CX plus KY, and J is an integer, so J is an integer. Alright, therefore, A divides C, and we're going to put a little box at the bottom saying that our proof is done. Alright, so let's look at this one more time here. Okay, so prove if GCD of AB equals 1 and A divides BC, then A divides C. Alright, so using this first section of the if statement, we were then going to assume GCD of AB equals 1 and A divides BC. Okay, using the Bezout's identity theorem relating to GCD, which we did previously before we erased this, we're going to be able to say that 1 equals AX plus BY for some integers x and y. Okay, then by definition of divisibility, again, which we defined previously here, BC equals AK for some integer k. Alright, and then getting to the note or the proof here, we know that C equals C times 1, and by substituting in with that first star, C equals CAX, or C equals C times AX plus BY, in parentheses there. Alright, using distributive law, CAX plus CBY, right, distributing the C to the first and then to the second. Alright. Bringing down the CAX plus BC in parentheses, y, just reordering so that we have a BC equals AK term here, all right? And then by substitution, all right, so let's put a double star here and then a double star here, knowing that, okay, this is where I was able to find this in my proof. This is where this part comes in, okay? So substitution, we substituted in the AK, and then by factoring out an A from both of these, we get A times CX plus KY, all right, which we just replace the CX plus KY with a J, and are able to say at the end that this proof is true, all right? Alright, so we're going to get started on this second problem. So the second problem, let's use black. Prove if x squared is odd, then x is odd. Okay. So to start, again, we'll go through all the different definitions that we're going to need for this problem. Okay. So first, all right, so the last proof, we just had a regular conditional statement, okay? But this one we're going to prove a little differently, all right? We're going to use a proof by contradiction. Or proof by contrapositive. Proof by contrapositive. Okay. So following how we do a proof by contrapositive, all right, we're first going to write out the conditional statement that we're going to follow as a guide. So in regular conditional statement, if P, then Q. Then Q. Okay. And that's just going to be denoted by these symbols. If P, then Q. All right. So when we're doing a contrapositive, we're going to say if not Q, then not P. Okay. And it's going to be with symbols like this. Not Q, then, if not Q, then not P. Okay, so that's our setup for a proof by contrapositive. The regular conditional statement of how we would do a proof, like we did in the last problem, if P then Q. All right, but we're going to do a little, I think the contrapositive would be easier in this example. So the contrapositive, if not Q, then not P. All right, if not Q, then not P. Okay. And we'll do one more definition. We're going to get the definition of even. Okay. So the definition of even, integer n is even if and only if n is of the form n equals 2k for some integer k. Okay. right, so definition of even, pretty straightforward right there. These two definitions are going to be key in our proof, okay? So I think we can now get started on our proof, all right, following these two. Just remember that these are going to be applied as we continue on with this proof above. Okay. So, prove if x squared is odd, then x is odd, all right? We're going to first say, all right, we're going to use a proof by contrapositive. All right, so excellent. Now, knowing that the conditional statement, if P then Q, all right, we're going to negate it and flip it. So we're going to say if not X, if not Q, so X is odd, all right, the opposite of odd, X is even. So if X is even, the negation of this statement, okay, then X squared is even. All right, so we're going to prove it this way. If X is even, then X squared is even. Okay, that's the proof by contrapositive we just set up. All right, so now knowing the definition of even that we just went over, we'll first assume this statement here. Assume X is even. Okay. By definition of even, X equals 2K for some integer K. All right. So let's star that again, knowing that this is going to be important later on. All right. Then, so we want to, our goal here, be able to say that x squared is even, okay? So we're going to say x squared equals x squared equals 2k squared, all right? And that's where the star comes in. We just substituted, all right, for the x here, and 2k right there. All right, so now when we put 2k to the power of 2, we're going to get 4k squared, okay? Excellent. Now, again, for this to be even, we want to be able to pull out a 2, all right? And we could do that for this problem. We're going to say, we're going to factor out a 2, 2k squared, okay? Exactly what we're looking to do here. Now, knowing that k is an integer, okay? 2 times an integer squared, all right? In this form here, we're going to also be able to say, okay, this is further again going to be an integer, okay? So we're going to say 2j, all right, where j equals 2k squared, and j is an integer. Okay, so knowing all this information, we could then say, thus, n squared is even, or x squared, I'm sorry. X squared is even, and it holds true that if x squared is odd, then x is odd. All right, I'll put a little box at the bottom there. Okay, and then we'll continue going on, and we'll reread this just to make sure it all makes sense here. Okay. So again, simpler way to do this problem. We're gonna prove it using a proof by contrapositive. All right, as we define proof by contrapositive. If x is even, then x squared is even. All right, it's negating these and flipping them or reversing the order. Okay, we're going to assume x is even, the assumption here, the if statement. All right, by definition of even, x equals 2k for some integer k. We start that knowing that, all right, when we go over this proof again, this is where this is going to be applied. All right, so knowing that our goal is to show that x squared is even, we'll then say that x squared equals x squared, right, with some parentheses there, all right, using substitution and replacing it, x squared equals 2k squared, okay, which then putting 2k to the power of 2, we're going to say equals 4k squared, all right, and knowing that we could factor out a 2 to get the even, we're going to say equals 2 times 2k squared in the parentheses there, all right. And since all the values in here are integers, we could say that equals 2j, where j equals 2k squared, and j is an integer. Thus, x squared is even, right? So this contrapositive statement is true. Then we could say it holds true that if x squared is odd, then x is odd. All right, back to that original conditional statement and that original proof that we wanted to prove for this problem. Okay? So we'll move on to the next one here. Okay. So the third one we're going to prove, we'll write it in black at the top. Prove x times 0 equals 0. Okay. Let's go through the definitions to start. All right. So first, we're going to do the additive identity. Okay. I'll write this in black. All right. So the additive identity is going to state an identity element that in a given mathematical system leaves unchanged any element to which it is added. All right, so a formal definition there. And now we'll just provide a little example, which is also going to be applicable to this proof. Okay, so 0 in whole numbers under the operation of addition. So let's use a whole number a, okay? Then under the operation of addition, plus 0 equals a, okay? An additive identity there. So any whole number that I plug in for a plus 0 will still equal a, okay? So on to the next property here. All right, we're going to go through the distributive property. Okay, so when we define the distributive property, we're going to show how it works. All right, so a, b plus c equals, all right, so a common term that a lot of people like to use, a double rainbow or distributing. All right, so we'll go through a double rainbow here, okay, which is just multiplying a by the first value, multiplying a by the second value. Okay, so when we do this, we're going to get ab plus, okay, so there's a separation of addition here, plus ac. All right, and that's the distributive property that we're going to use, all right, as we go through. Okay, so these two so far, additive identity, distributive property. We'll go through the additive inverse. All right, so when we're going over the additive inverse, we're going to say that the additive inverse is a number that when added to a given number equals 0. All right, so we'll say that this number, we'll give it a value of a plus a number here, all right, so we'll write this in parentheses, equals 0, okay? So an actual number that we'll plug in, let's say it's 2 plus something equals 0, all right? So when we're using this, for this example, 2 plus -2 equals 0, okay? So when we're putting it back into this formal definition here, a plus -a equals 0, okay? Now the additive inverse is this -a here, okay? Which then we're going to use again in our proof, okay? So these are the three that are very important for us, all right? Okay, so going to the proof, we're going to start by saying since 0 is an additive identity, in addition, under addition, under the operation of addition. So we're going to say x times 0 equals x times 0 plus 0, okay? And then using distribution, we're going to say equals x times 0 plus x times 0. Okay? This is using by, forgot to include the n, then there, by distributive let's give myself a little more room here. By distributive property. Okay. Now, we're going to say that then by additive inverse, we add negative x times 0 to both sides. To both sides. Okay. That's going to say x times 0 plus negative x times 0 equals x times 0 plus x times 0 plus negative x times 0. Okay? So, then, since x times 0 plus negative x times 0 plus x times 0 equals 0, then since we're gonna then replace the different parts of this. So we're gonna say, okay, negative x times 0 plus x times 0 equals 0, all right? And where is that in this above statement? It is right here, and also right here, okay? So we're just gonna replace that with 0, okay? So 0 equals x times 0 plus 0, all right? And this again looks similar to something we did before, right? So if we look up here, all right, similar to this, okay? So we said x times 0 equals x times 0 plus 0, all right? Exactly what we have here. So we're then going to substitute in equals x times 0. And that leaves us, bringing this down again, that 0 equals x times 0, okay? So we'll add a therefore, zero equals x times 0, okay? And that's exactly what we wanted to prove here. Therefore, we're going to add this box to say that our proof is done, okay? And we're going to go through this one more time, just to make sure for clarity, okay? Since 0 is an additive identity under the operation of addition, then x times 0 equals x times 0 plus 0, all right? Distributive property with the x equals x times 0 plus x times 0, all right? So we use the distributive property there, is distributed the x to both the zeros, all right? Then, by additive inverse, we add negative x times 0 to both sides, okay? So, exactly what we had here, x times 0, this, these, and these. We then bring it down, okay? X times 0 plus negative x times 0 added to the left side, all right, equals x times 0 plus x times 0, all right, we had there, plus negative x times 0, okay? Then, knowing that negative x times 0 plus x times 0 equals 0, okay? 0 equals x times 0 plus 0, therefore 0 equals x times 0, all right? And this, okay, is due to the additive inverse. By additive inverse. Okay? We explained it before, we explained it there, but just want to make sure that's how we know that this is true. Okay? Alright, and therefore 0 equals x times 0, and we are done. Okay? So that was number 3. Alright? Alright. So going on to number 4, okay, this one's going to be a proof by cases. We'll explain what that is in a second. Alright? Prove x times y equals 0 if, that's our if statement. Prove if x times y equals 0, then x equals 0 or y equals 0. Okay? So we'll go through again the definitions first. All right. The first one we want to cover is the multiplicative inverse property. Inverse property. Okay? And that's going to say a number, let's say A, has an inverse, or we can also call it a reciprocal, if and only if A times R equals 1, where R equals 1 over A. Okay? So R is that reciprocal for this problem. A is a number that we're going to use to show the example. All right, so A times R equals 1, where R equals 1 over A. All right, it's going to be very important as we continue on to this next one. Okay, now we're going to go over the definition of rationals. All right, so rational numbers is a number that can be expressed in the form P over Q for some integers P and Q. Also, Q is not equal to 0. Okay, so we can't have Q in the denominator. Or we can't have a 0 in the denominator. All right? Let's go through the definition of irrational. So an irrational number is a number that cannot be written as a simple fraction. So some famous examples of irrational numbers, okay? Examples, we're going to say pi, all right? And we can also say radical 3, all right? There's many more, all right? But irrational numbers, they do not stop and they do not repeat, okay? So that's what makes an irrational number very unique, all right? The next number we're going to go over is real numbers. Okay. So, actually, just going back to rationals. Rationals are going to be expressed using the symbol Q, okay? And real numbers are going to be expressed using the symbol R, okay? So, real numbers are the set of all rational and irrational numbers. All right. So when we're talking about real numbers, okay, this is an N. All right, when we're talking about real numbers, we're saying, all right, rationals, a number that can be expressed in the form P over Q. All right, we're saying irrational, a number that cannot be written as a simple fraction. All right, and those two combined give us a real number. Okay, so these are the property and numbers that we're going to use to prove this problem. Okay, the sets of numbers that we're going to use to solve this problem. Okay. So again, similar to the last problem, or similar to other problems we've done already, we're going to say our conditional statement, all right? We're going to assume, we're going to use our conditional statement and assume x times y equals 0. Okay, so that's the first part right up there. We're also, let's take it back a step. All right, so prove if x times y equals 0, then x equals 0 or y equals 0. All right, so this problem is going to require a proof by cases. So when we're saying a proof by cases, okay, we're saying that the proof is going to be broken down into 2 or more cases, and to prove that this claim holds true in every case, okay? So for this example, we're going to have 2 cases, x equals 0 or x does not equal 0, okay? But proof by cases, the problems can have many different cases, all right? This one will just need 2, all right? So we will use a proof by cases. Okay, and we're going to let x, y be real numbers. Okay. We're also going to assume x times y equals 0. Okay? So, looking at this problem, the two possible cases are x equals 0 or x does not equal 0. Okay? So we'll start by going over case 1, which will say x equals 0. Okay? So similar to the last problem we just did, all right? We're going to bring this conditional statement down. We're going to say then x times y equals, using substitution, okay, for the x, equals 0 times y, okay? And we know that from the last problem we did x times 0 equals 0, then y times 0 will also equal 0, okay? In this case, the statement holds true. The statement, let's reiterate our statement here. The statement x times y equals 0 holds true. All right, could put a little check there. All right, we're good. Okay. So now, case 2. Okay. X, let's go back to the green. X does not equal 0. Okay? X does not equal 0. All right, so to start, since x and y are real numbers, then the multiplicative inverse property holds true. Okay? So using the multiplicative inverse property, we will take x times y equals 0 and multiply both sides by 1 over x. Okay? Now, we're going to say note. All right? So multiplying both sides, 1 over x times x times y equals 1 over x times 0. Oh, you know, let's make some more space for ourselves. All right. Let's see if we can put it right down here. Note 1 over x times y equals 0 times 1 over x. Okay? So 1 over x times x, from this we're going to get 1 times y equals 0. Alright? Now, any number times 1, we'll just give you that number again. Y equals 0. Okay? So, excellent. If x does not equal 0 in case 2, then y equals 0, exactly what we're looking for up there. Alright, for our case 2. Okay? Thus, x times y equals 0 holds true if, no, not if, then, I need more space. Okay. Then x equals 0 or y equals 0. Let's correct this statement down here. All right, that doesn't sound like what we're looking for. Okay. Let's say hence if x times 0 equals 0, then x equals 0 or y equals 0. Okay? Case 1, case 2. Alright, so let's just read. We've got to put a little x here, or a little box here. Say, alright, end of the proof. Alright, and let's just go over it one more time. Alright, so prove if x times y equals 0, then x equals 0 or y equals 0. Alright, we're going to follow a proof by cases. Okay, we'll use a proof by cases. Let x, y be real numbers. Okay, so it could be rational or irrational. Alright, assume x times y equals 0. This is the if statement. Okay, the two possible cases are x equals 0 or x does not equal 0. Okay, filling in case 1, x equals 0. Then x times y equals, substituting in the x, 0 times y equals 0. In this case, the statement holds true. The statement x times y equals 0 holds true. All right, give that case a check. That works. Case 2, x does not equal 0. Since x and y are real numbers, then the multiplicative inverse property holds true. Okay, so we take x times y equals 0 and multiply both sides by 1 over x. All right, the note, the proof, the additional needed information for this, we're going to say 1 over x times y equals 0 times 1 over x. All right, since we said we're going to multiply both sides by 1 over x. 1 over x times x. All right, 1 over x is equal to the reciprocal. Okay, then this is going to give us 1 times y equals 0. All right, and y times 1 equals 0. All right, hence, if x times y equals 0, then x equals 0 or y equals 0. Okay, let's move on to number 5. Okay. All right. Number 5, prove. Let's start left corner. I need this space here. Prove log. base 27 of 14 is irrational. Okay, so we know before, all right, we used irrational, all right, a number that can't be simplified into a fraction, okay. We also know what rational is. We can put it into a fraction, p over q. The denominator is not equal to 0. All right, but for this proof, all right, we're going to introduce something new. We're going to introduce a proof by contradiction. Okay, proof by contradiction. Okay, so again, we'll just reiterate that original conditional statement. Okay, if P, then Q, all right, P to Q, all right. So now for the contradiction, we want to find something. Okay, we're going to say both P and Q. Okay, so both P and not. And not Q. So P and not Q. Okay. This is the statement we're going to use, P and not Q. All right. So we want to try to prove okay. So to demonstrate the proof by contradiction, we're trying to prove we're false. Then this would lead to a statement which is known not to be true, a contradiction. Okay? All right. Let's move on to the next part here. All right, a logarithmic function. Okay. For y greater than 0, b greater than 0, and b not equal to 1 if y equals b raised to the power of x, then x equals log base b of y. Okay? So y equals b to the power of x is the exponential form. All right. X equals log b log base b of y is the logarithmic form. Okay? So logarithmic, the short way of saying it is log, okay? And these are both going to be used in our proof here, okay? So let's get started on that. All right. So we're going to use a proof by contradiction. let's rewrite this statement. Okay. We're going to assume or we're going to say the proof by contradiction, log base 27 of 14 is rational. Okay, so assume log 27 of 14 is rational. Let x equal log base 27 of 14, where x is a rational number. Okay. By definition, of rational, x equals p over q for some integers p, q. Also, q is not equal to 0. We can't have denominator be a 0. Okay? So, continuing on by substitution, log base 27 of 14 equals p over q. Okay. From here, we're going to use definition of logarithmic function. Okay. Function. All right. We're going to then say 27 raised to the power of p over q equals 14. All right. And then multiplying both sides by the power of q, we get 27p equals 14q. Okay. So raise both sides, we'll write that. Raise both sides to the power of q. Raise both sides. Multiply both sides. Alright. Multiply both sides by, okay, multiply both sides by the power of q. Okay, multiply that side by q, and that's how we're able to get q out of the denominator there. All right. Good. Okay. Note p, q are both integers where p is greater than 0 and q is greater than 0. Okay. Now using log base 27 of 14 equals P over Q. We know log base 27 of 14 is greater than 0. So that's an S. So P over Q is greater than 0. Okay? Right, using this here. Okay. We brought it down. Let's add a different color star so we know. Okay. All right. Now, using using 27 power of P equals 14Q. Okay. We know, if P is greater than 0 and Q less than 0, okay, to create our contradiction, then 27P is greater than 1 and 0 is less than 14Q is less than 1. Okay? Alright. Star again. We'll double star it. Double star it. Okay? So that's where we know where we got that section from. Okay? So we know that this has to be a contradiction because P and Q have to be the same sign if P over Q is greater than 0. All right? So we're going to write that. This is a contradiction. This is a contradiction. P and Q must be the same sign if P over Q is greater than 0. Okay? So why is this the case? Okay. It looks like I just wrote panda. Let's just correct that. P and Q. All right, a little neater. There we go. All right, this will yield two different unique prime factorizations. Okay, prime, let's rewrite it again. Prime factorizations. Okay, so our proof by contradiction, all right, log base 27 of 14 is rational, all right, that was a contradiction. Therefore, we're going to say, thus, log 27, log base 27 of 14 is irrational. All right, and look at that. We still have the box there. All right. Okay. Ran out of space, a little bit of a longer proof. Let's just go over it again. Okay. So proof by contradiction. All right. Log base 27 of 14 is rational. All right. Assume log base 27 of 14 is rational. All right. That's our assumption there. Let x equal log base 27 of 14, where x is a rational number. All right. By definition of rational, x equals p over q for some integers p and q. All right. Since we can't have a 0 in the denominator there, q is not equal to 0. All right. By substitution, all right, knowing that x equals log base 27 of 14, we're going to substitute in p over q. So log base 27 of 14 equals p over q. By definition of logarithmic function, which we went over, showing the exponential form, the logarithmic form, 27 raised to the power of p over q equals 14. Therefore, when we multiply both sides by the power of q, 27 raised to the power of p equals 14 raised to the power of q. Okay. Note, p and q are both integers. P is greater than 0 and q is greater than 0. All right. So using, again, showing the star, awesome. Using log base 27 of 14 equals p over q. We know log base 27 of 14 is greater than 0, so p over q is then greater than 0. All right. Using 27 to the power of p equals 14 to the power of q, all right, where we got that right there. If p is greater than 0, okay, and q is less than 0, our contradiction, then 27 to the power of p is greater than 1, and 0 is less than 14 to the power of q less than 1. This is a contradiction. P and q must be the same sign if p over q is greater than 0. This will yield two different unique prime factorizations. Thus, log base 27 of 14 is irrational. All right. Let's move on to number 6. Okay. We're going to go over the fundamental theorem of arithmetic. Okay. So this is also expressed using the acronym FTA. Okay. All right. So the fundamental theorem of arithmetic says for any positive integer n greater than 1, there is a unique prime factorization in such a form n equals p1 1 raised to the power of E1 times P2 raised to the power of E2 times P3 raised to the power of E3. All right, and that can keep going on until we get PK raised to the value of, raised to the power, all right, of EK. Okay? All right. So, we're going to continue on. Where P1 less than P2 less than P3, all right, all the way up to PK less than PK, and P1, P2, P3, all the way to PK are prime numbers. All right. We'll go through the definition of prime after this, okay? Kind of important for this problem, all right? Also, E1, E2, E3, all the way up to EK are positive integers. Okay, so we'll go through the definition of prime numbers. All right, and we'll also show an example, okay, using a tree method, okay? So, we'll go prime numbers. And the definition of prime number, we're going to say, is a whole number greater than one whose only factors are 1 and itself. Okay, so some of the prime numbers, all right, that we can go through, use, and go and test out when we're going through a problem like this. Okay, we'll just write out that they include 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, and so on. Okay? So these are the prime numbers. All right? Then we're going to go through, also we'll go through the definition of a factor. All right? Further important in this problem. Whole numbers. So a factor is a whole number, or whole numbers. Factor is whole numbers. Whole numbers that are multiplied to produce another number. Okay, so we have the definition of factors here. All right, now to give an example of the fundamental theorem of arithmetic, all right, we're going to use a factor tree. Okay, So we'll take note of all the stuff we have here. All right. Now the factor tree. We're going to be able to find all the prime numbers, what they raise their power to, in order to get another number. Okay, so factor tree. All right, for this example, let's use 4, 3, 1, 2. Okay, and again, let's note these different primes that we have. Okay, so let's move this number over. 4, 3, 1, 2. Okay, so the primes, we have 2, 3, 5, 7, 11, 13, and so on. All right, these are all the ones that we'll need for this problem. Okay, so first, we're going to try to find two factors, all right, one being a prime, that are going to multiply together to get this number. Okay, let me grab my, I can do this actually. Okay, so we know this is even. Okay, so 2 is one of the factors. All right, and then we're going to get 2, 5, 1, 6. Okay, then again, also, we can use that 2 again. All right, and we're going to get what are we going to get here? We're going to get 2, I need a calculator. No. Okay. All right. So this goes in 12. All right, 24. 1. Bring the 16 down. All right. Then we're going to get 5. Okay. And then 16. And then we're going to get 8. Okay. 1, 2, 5, 8. All right. Again, this is an even number. Okay. So we're gonna divide 1258 by 2 again. Okay. Again, divided by 2. We're gonna get 6. Okay. 12. Cancels out. Bring down the 58. Okay. We're gonna get another 2. Okay. We're gonna get 18. And then a 9. Okay. So 6, 29. All right. Okay. So continuing on. All right. 629. Let's see what we could divide 629 by. All right, so it's not an even number. All right, so we can't divide 629 by 2. We might be able to divide 629 by 3. All right, let's see if we could do that. All right, so we'll get 2, 29. Oh, looks like we'll have a remainder. All right, so we can't do it by 3. All right, could we do it by 5? No, not by 5. Can we do it by 11? What about 7? No, 7 won't work either. 11? Maybe 13? Let's see. All right, let's write out some more here. All right, 17. We have 19, 23, 29. Okay. Continuing on. 31, 37. Let's see. Let's try 629. Let's see if I made a mistake here. All right, I'm gonna restart. All right, maybe I would, no, I want to stick with this one. I like the challenge of this. Okay, so again, we'll do the factor tree. Okay, so we want to find all the prime factors of 4312. All right, 4,312. All right, so we'll write out all the prime numbers. Okay, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31. So, finding the prime factorization of 4,312. Okay? So first, we know 2 works. Okay? 2. All right. That might have been my issue before. 21. Okay. So minus 42. 1. Bring down the 1 and the 2. Okay. Now we're going to get 5. 1. Alright, bring down the 2 again. Alright, and now we're going to get 6. Alright, that was my issue the last time. Okay, so that definitely makes sense why I was having some trouble there. Okay, so again, this is an even number. We could then divide it by 2 again. We're going to get 10 minus 20, 1, 5, 6. All right. We're going to get, no, I'm not going to get 4. We're going to get 7. All right. Minus 14, 1, 6, and we're going to get 8. All right, so, and 2. Excellent. Okay. Still, again, an even number. All right. So, we're going to again multiply or divide it by 2. Five, okay, minus 10. All right, so then we're just going to bring down the 7, bring down the 8, okay. And then from there, we're going to get 39. 39 times 2 equals 78, and that is our next. Okay, part of the tree that we'll add in here. Okay. So 539 is not an even number. Okay. 539. Can it divide by 3? No. Can it divide by 5? No. Can it divide by 7? I believe so. Let's try it here. Okay. We'll get a 7 minus 49 equals 4. Bring down the 9. All right. Again, 7 there. Excellent. So we'll get 7. And we'll get 77. All right. 7 being the prime. Okay. Now this one's very simple here. 7, 11. Okay. 7 times 11 will give us 77. Exactly what we're looking for. Okay? So when we're going to write this final answer in, again, following all the rules of what we just posted in the definition before, all right, we're going to put 2 cubed times 7 squared times 11. Okay? Now when we're checking this just to make sure, we could say 8 times 49 times